Welcome back to a new video about inverse Chebyshev response filters using the LC ladder filter configuration. We will look at the high-pass filter design in this second example. Of course, we will work out our calculation step by step and verify these in SPICE simulations. So let's look at our problem. Our objective is to design an inverse Chebyshev response, also called the Chebyshev response or Chebyshev type 2 response, of a LC ladder configuration for a high-pass filter, and we will use 50 ohm double terminated shunt input circuit. As discussed before, this is the generalized circuit. These are the normalized values for the source resistor and the load resistor. Specifications are the following. For this high-pass filter design, the maximum passband ripple must be 2.5 dB, the minimum stopband attenuation must be 60 dB, and the passband frequency is 2.5 megahertz, and the stop band frequency must be 1 megahertz. So let's see how we can solve this problem. So in the solutions, we take the first step is the calculation of the filter order N for this high pass filter. We go with the specifications from the A max and A minimum first, looking at the epsilon. Epsilon P is related to A max, which is in this case 2.5, or A max, which is 2.5 dB, and when you calculate this, you get 0.8822 approximately. Epsilon S is related to A minimum, and A minimum is 60 in this case, so you just substitute the values, and you get now almost 1000, so 999.99, so very close to 1000. Now, when you take these two values, and also the passband and the stop band frequency in this formula, you will now get 4.9312, which is in integer form 5. So we need to have a fifth order high pass filter using this inverse Chebyshev response characteristics. Okay, now when you now look at the second step, which is the calculation of the frequency scaling factor, which is KF, which is actually not a calculation, but it is a setting. So we just set the KF to the omega s, which is now this 2 pi times 1 megahertz. So that will be then 2 pi times 10 to the power 6. And that will be then exactly, in this case, 1 megahertz. So we will use this value for our calculation of the component values. Now the step 3 is actually the calculation of the component values, which are the scaled component values for our final design. Now this is a table for the inverse Chebyshev response for a filter order of 5, and it is for the LC ladder low pass filter normalized element values, not for high pass, but we will make the transformation from the low pass circuit to the high pass circuit. It's double terminated, and it is now normalized for stop band frequency of 1 radians per second. Okay, so what do we see? Now we need a 60 dB as our minimum stop band attenuation. So you look actually at this column, and you see actually this row here, which is at number 8, and that is actually what we need. And these are the parameters for C1, C2, L2, C3, etc. what we need to use for our final design. Well, what does it mean actually, all these values here? Now the prototype circuit low pass again is this circuit. You see the RS and the RL again, and in between these components is our generalized filter. The C1, L2, C2, etc. is actually following this order. So C1 is in the normalized form, has a value of 1.18689 farads, because we need to look at this order, this row, and C2 will have then 0.26612 farads, and L2 will have then this much Henry, so 3.39890, etc. So every value is actually shown here in the normalized form. But we need to, of course, look at our actual design, which is our scaled values. So we need to first make the transformation from the low pass to the high pass filter, which is actually changing each capacitor into an inductor and each inductor into a capacitor. That is actually shown here. And also use the primes here to designate that is scaled. So it is actually going to the what we wanted, not the normalized value. So you see actually RS, for example, is scaled. So it will be then scaled from 1 ohm to 50 ohm, because it's already set. That's also valid for the load. And you see also the capacitor C1 is changed to L1, capacitor C2 is changed to L2, and the capacitor C3 is also changed to L3. So actually you see all capacitors change, and also the inductors hence change. So this is a capacitor, this is a capacitor. This is also called the minimum capacitor design. This is actually a minimum. I mean, this is a minimum inductor design. This is a minimum capacitor design because you have here more inductors than capacitors. So we need to determine now all these component values. So let's then continue and make some space here and also only use this part what we want. This is actually this row. So what is now the L1 prime and L2 prime, etc. Now L1 prime is calculated using the value of C1 from the table. That's 1.18689 approximately, 9 approximately here. And the Km is 50. Why? Because it is double terminated with the 50 ohm input circuit. So that is actually what we use as Km. That is our magnitude scaling factor. The Kf was 2 pi times 10 to the power 6. You see all these things here. So that will then give us this value of 6.705 microhenries. L2 in a similar form, but I'm only looking at the C2, and C2 is here, 0.26612. That's shown here, and then you will get now approximately 30 microhenries. Moving on to C2 prime, which is actually going to the L2. That's shown here. Everything is actually in a similar form, but then you look at the coefficient of L2, and you get now here 936.5 picofarads. Now moving on to the next is the L3, which is looking at C3. So C3 is here normalized 4.5131. Again, the Km is 50, and the Kf is again what we want, what we have set in step 2. Now moving on, a similar form for L4 prime, C4 prime, and also L5 prime. These are now the component values for the capacitor and inductors in the circuit. And now the RS prime and RL prime are the normalized values times 50, because the Km was 50. So 50 times 1, that will be then 50 ohm in the final design, and then 50 times 1, again 50 ohm. So RS prime and RL prime are 50. Okay, now we have our components. Let's now bring these here together in the list. And also our design circuit. This circuit here is the prototype low-pass filter, and this circuit here is our design final circuit, high-pass filter 5th order, inverse Chebyshev response. You see again the transformation from the capacitor to the inductors, etc. Okay, let's now look at the simulation results for this circuit. This is the magnitude plot for in our body plot. You see some parameters and some labels, so let's go one by one. First one is the passband gain, which is minus 6.0206 dB. This is indeed correct. Why? Because at high frequency, so high frequency gain, it is 0.5 the gain, because you get a 50 ohm here and a 50 ohm there, and this circuit is actually considering as a unity. So you get now 50 over 100, that is actually 0.5, so this is indeed correct here. You see actually also the proof here. The gain is minus 8.1371 dB, you can also see that here, at 2.5 megahertz. And the ripple there, or the decrease there, you can calculate that from this baseline is 2.1165 dB, which is less than the 2.5 dB, because this was maximum allowed. So this also according to specifications. That's actually shown here. Now the next one is stop band attenuation, which is here. It is a little bit over 60 dB, but we want minimum stop band attenuation of 60 dB. So, and that is looking at the 1 megahertz. So that's also according to specifications. Now, in addition, we see the cutoff frequency here, which is not a specification, but we can look at it. So going from this baseline down by 3.0103 dB, you can see that it is happening at 2.3961 megahertz. But how can we calculate this? Now, the cutoff frequency can be calculated for this high-pass filter using this formula. You see the Fs again, and also the cosine hyperbolicus and arc cosine hyperbolicus with this epsilon, as we have determined from analysis, and also the filter order n. We know the filter order, we know the epsilon s, which is all known, and the Fs is here 1 megahertz. So when you now substitute the values in here, you get now almost 2.4 megahertz, as we see also here in the label. So that is again a proof that this is indeed correct. So everything is checked here and according to specifications. Alright, this is our example number 2 about the inverse Chebyshev response using the LC ladder configuration for this high-pass filter. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video.